right, so we're going to talk about what's called the mass volume relation, which essentially is very simple. It says the mass times the volume of the white dwarf is a constant. And what that means is if you add mass to a white dwarf, it shrinks, it gets smaller. Essentially because if you add mass to it, you make gravity stronger, so the degeneracy pressure needs to get bigger in order to balance that. And it works out that in order to pull that off, the white dwarf needs to shrink in order to raise the degeneracy pressure to keep up with the additional gravity. So let's derive that relation in an approximate way. So the mass, this is minus, it's the mass dash volume relation. Dash, dash. Dash, dash.
I accidentally wrote mass dash.
Use very common abbreviation WD for white dwarf. WD, WD40, WD. We add mass to a white dwarf. Say the internal gravity gets stronger. So P needs to rise to maintain equilibrium. It turns out this means the white dwarf volume shrinks, as we will now justify. It won't be an exact derivation, but good enough to show that it ought to happen. This is very significant because it means that if the white dwarf is in a companion system that has a star that's dumping mass onto the white dwarf will shrink over time as a result. That means it's converting gravitational potential energy into thermal energy and radiation. That means the white dwarf's internal temperature is rising. And if enough mass is added to it, the internal temperature can reach the ignition point for carbon, and the white dwarf blows up as a type 1a supernova. So it's tied to the fact that a white dwarf shrinks when you add mass to it. So again, this is going to be a rough derivation, if you will, using the equation of hydrostatic equilibrium under the unrealistic assumption of constant density throughout the white dwarf. So we're making that assumption, which is not realistic. We can obtain an estimate of the central pressure as follows. Using the equation of hydrostatic equilibrium. Under the unrealistic assumption of constant density, certainly the white dwarf is denser at its center than it is at its surface, because it's compressed by the overlying layers. So this is a back of the envelope calculation, as they say. We can obtain an estimate of the central pressure. factor, but it's not going to be way, way off. It's that kind of idea. Remind you, there's the equation of hydrostatic equilibrium, that the pressure gradient is minus g m of r over r squared rho. Rho is the local mass density, so that's mass per unit volume. G m of r over r squared is the local value of the acceleration due to gravity, which, because of spherical symmetry, says we only care about the mass interior to radius r within the star. So m sub r is the mass enclosed within radius r. Big G times that mass divided by the distance from the center squared is the local acceleration due to gravity. So this says pressure force per unit volume is equal and opposite to the local value of the mass per unit volume times the local acceleration due to gravity. So that's the equation of hydrostatic equilibrium. Now, if we assume that the density is constant, then the mass per unit, then the mass m sub r will just be that constant density times the volume of that sphere of radius r. 4/3 pi r cubed rho, in other words, will be m sub r. Mass per unit volume times the volume of the sphere of radius r. So in other words, this becomes minus g times m sub r is 4/3 pi r cubed times rho. Mass times, volume times density equals mass, divided by r squared times rho, because rho is still out there on the right side too. So you get minus 4/3 pi big G rho squared r. Simplify. Okay, any questions? Does that make sense? On board here? On board, ready for the next step in the current exciting derivation.
That's on the board time.
So, the big R being the radius of the white dwarf. The pressure at the surface, P of big R, minus, I'm sorry, that's not what I'm going to say. The pressure at radius little r inside the white dwarf minus the pressure at the surface, P of big R, should be, integrate that equation. Right? You've got an equation for dp dr, So if you integrate dP dr, you get the change in the pressure. So that will be the integral from big R to little r of dP dr. Right, the integral of the derivative is between two limits is the change in the function between those two limits. Well, we've got our expression for dP dr over there. So this will be equals 4/3 pi g rho squared times the integral from little r to big R of r dr. In other words, I flipped the limits in order to get rid of the minus sign in the expression dP dr over there.
Those are hard intro.
It's this, yeah, so, right, so, Mathematica, right?
I'm not even sure mathematically what that one.
I don't think it has enough time.
Yeah, it's got better things to do. Is it next?
It's like a little one.
Yeah, maybe Wolfram Alpha will be going to help you with this.
Too hard.
So, yeah. So this will be 2/3 pi g rho squared times big R squared minus little r squared. Just plugging in the limits, of course. Using the integral is half of r squared. It should be reasonable to say that the pressure goes towards zero at the surface of the white dwarf. So if we set the outer pressure being equal to zero, then we find that P at radius r should be 2/3 pi g rho squared times big R squared minus little r squared. So in other words, I just said this was the difference between P of little r and P of big R. If P of big R is 0, then this is P of little r itself, being that expression right there. So if we want to get what's the central pressure, we can just plug in little r is equal to 0. And that'll be our approximation because we made an approximation of constant density. The central pressure should then be, for little r equals 0, central pressure is then, we'll call it P sub z. C is approximately 2/3 times pi times g times rho squared r squared.
It's the half-life finals.
What?
I'm excited because it's the half-life finals.
Oh, which one?
For snowboarding.
Yeah.
I think that's good
Isn't
work.
there a
Says
John
on
Michael.
Michael.
Yeah, she told us.
I'm so excited.
Yeah,
Oh, yeah,
yeah.
Kim.
Yeah.
Yeah, Chloe Kim, yeah.
Yeah,
did the-
that's really-
yeah. It's actually, it's great because, you know, she's in Korea and her family is from Korea. You know, her dad's actually an immigrant from Korea. And so, you know, she's very much an American, but her dad, you know, is an immigrant from Korea, so it's like perfect, you know, that she goes and gets a gold medal over there.
Stimulus Koreans, man. Okay.
I was listening to her getting interviewed yesterday, and I'm thinking like, what is she, like 17 or something like that? And I'm like, yeah, you're totally 17, just listening to her talk, you know, it's pretty funny.
We did love the little tweets about food. Like she was, like between runs, she just tweets about food.
Oh, yeah, oh, yeah, 'cause she said she was hangry.
Oh, just one goal. Now I'll have to get some, building a goal.
Third run, I need a shirt. Something like that.
I mean, she can win gold, she can eat as much food as she wants.
Yeah, just keep it up.
She can do whatever she wants. Oh,
That's right, I think she's earned it. All right, so in the spirit of our approximations, we'll just set that equal to our expression for the degeneracy pressure, and then go from there. By setting this equal to the degeneracy, our expression for the degeneracy pressure, we can use that to estimate the white dwarf's radius. We can estimate the WD's radius, R. So we could write that 2/3 pi g rho squared r squared is equal to our expression that we got before of 3 pi squared to the 2/3 power over 5 times h bar squared over me times the quantity c over a times rho over the mass of a hydrogen atom raised to the 5/3. We could solve that for r after setting that rho was the mass of the white dwarf over 4/3 pi r cubed, the total radius, in other words, the mass of the white dwarf divided by its volume, will be its constant density, consistent with our assumption of constant density. So, result after some painful algebra, but then I'm going to show you how to get the result much quicker, the result we really want. But notice, if we actually do turn the crank here, which is kind of pointless because we've made it a lot of approximations, the result after some painful algebra is that the radius of the white dwarf is approximately, since we made a bunch of approximations, 18 pi, the quantity to the 2/3 over 10 times h bar squared over the gravitation constant times the mass of the electron times the mass of the white dwarf to the 1/3 power times that quantity z over a, well actually now it's just 1 over mh, because we have substituted for the density, all to the 5/3 power. Yeah.
Obviously.
Yeah.
Just falls right in.
Mm-hmm. Again, in a minute I'll show you how you actually you can get the result we want very quickly without, if you just don't worry about all the constants. But we'll just show what you get when you do that. says R times m to the 1/3 is constant, because if I pull that m to the 1/3 over, everything else in there is a constant for a white dwarf. In other words, there's the mass of a hydrogen atom, the mass of an electron, the gravitation constant, 18, pi, and 10 are all constants. And then z over a for a given composition of the white dwarf, that's a constant too. So the radius times the mass to the 1/3 is a constant. Cube both sides, and that says the mass times the radius cubed equals a constant. But the volume is 4/3 pi r cubed, so that says the mass times the volume is a constant. Not the same constant in each case, I have things multiplying it, but whatever. Mass times volume is constant, is the result of all that. Cool. If we can get that without doing the painful algebra.
I just noticed,
What's that?
everyone in this room is wearing glasses except me.
Huh. Oh, there you go. Oh. You had to come back for that.
Sorry, that was just a little observation.
I see.
But
Okay.
I don't even have a joke for that.
it was just that stupid, you can't add to it.
Right. So we can get that actually, just if we look at this original relationship right here. So let's take the rho over to the other side, and then everything else is a constant in there. And now everybody has glasses. So take,
I wish I had turn around.
yeah. Right. Take the rho over to the other side, move the 2/3 pi g over to the other side, and what we get is that rho to the 1/3 r squared is a constant. Because here's an r squared, and rho squared divided by rho to the 5/3 is rho to the 1/3 power. Right? 5/3 minus, rho squared is rho to the 6/3, so if I divide by rho to the 5/3, I get rho to the 1/3, and then everything else in there is a constant that I can take over to the right-hand side of the equation. Because the painful algebra consists in all these constants and all that that are being carried. So if we don't care about that, all we say is just lump all that out together and call it a constant, then rho to the 1/3 r squared is a constant, but rho is equal to the mass divided by 4/3 pi radius cubed. So what I can do is I can say that mass over radius cubed, well, what do I want to do? So first I'm going to, I guess, not to skip a step, let's cube both sides. So this is rho r to the 6th equals constant. And again, I'm not going to keep renaming the constant, I'll just keep saying constant. But rho is mass over 4/3 pi r cubed. Throw the 4/3 pi into the constant, so this is mass over radius cubed times radius to the 6th is another constant. Or in other words, mass times radius cubed is equal to a constant. Boom! Mass times volume is constant. Boom. So the mass times the volume is a constant. If you double the mass, the volume would be half as big. If you triple the mass, the volume would be 1/3 as big. The more mass of the white dwarf, the smaller it is in radius, is what it comes down to. So, in particular, the volume and the mass are inversely proportional to one another. Okay, any questions? So now we're ready to talk about the famous Chandrasekhar limit, the maximum mass for a white dwarf, such that if you go over that mass, then you can't have a white dwarf anymore. Electron degeneracy pressure won't do the trick. And so the next step up, assuming it doesn't blow up first, is a neutron star. So if you have a white dwarf already formed, and you add mass to it, it blows itself up as opposed to forming a neutron star because it's a match waiting to be lit because it's carbon which can fuse. But if you have the core of a massive star that's made of iron, remember iron can't fuse, and so if the iron core is too massive, it turns into a neutron star instead of a white dwarf, is what it comes down to. So, in fact, it's massive star always turns into a neutron star, is what it comes down to. The remnant's always big enough to turn into a neutron star. So, let's talk about the very famous Chandrasekhar limits. So I think I've mentioned before, that my lovely wife, when she was in graduate school, almost became a computer for Subramanian Chandrasekhar. I never know if it's Chandrasekhar or Chandrasekhar. I need to ask the person I had before, and I forgot what they told me. As in, not the kind where she wouldn't have gotten any credit. She would have gotten credit for what she was doing, but in other words, he had some tedious calculations that he didn't feel like doing, and so he wanted a grad student to do it, and my lovely wife was invited to do so. So she was almost a computer for Chandrasekhar.
Why did she not do it?
I don't remember exactly. I think he just changed his mind or something like that. Yeah.
Fine, I'll do it myself.
What's that?
I said, fine, I'll do it myself.
Fine, I'll do it myself, yeah, basically. And these days you would hand it to Mathematica, you know. Like, Mathematica existed when I was in grad school, but it wasn't as widely used at that point. So, it dates back to the 80s, as a matter of fact.
Oh. Good. It's asking me for an application, but it's not giving me an error.
What?
Our Mathematica on our laptops started throwing us this error whenever we started it up. It's a serious startup error, and couldn't figure out what to do with that, so I re-downloaded it, and now it's asking me for an activation key, which I think I can find.
Yeah, I imagine you can, yes. So notice that the mass-volume relation seems to imply that as you keep adding mass, the volume keeps getting smaller and smaller, and in the limit that you went to an infinite amount of mass, the volume would shrink to 0. Well, we already know you'd eventually turn into a black hole, even if this relation were true. But in fact, what this relationship assumed is that the expression we got for the pressure was correct. And if you think back to when we wrote that expression for the pressure, we used p squared over 2m as the kinetic energy. We used the classical expression for kinetic energy. But what happens as you keep shrinking the white dwarf is that eventually the electrons are going faster and faster, so that you need to take into account the effects of relativity. Yes. Once the electrons start getting close to the speed of light as to how fast they're moving, then we have a crisis, if you will, because there's a speed limit here, and once they're close to the speed of light, you can't really get them to go any faster. So as a result, you no longer have the same expression for the pressure anymore. They've kind of topped out at a maximum speed. And so that limits the ability of the pressure to rise anymore, and that's what leads to the Chandrasekhar limit. It's when the electrons become relativistic that they're not able to keep increasing the pressure when you keep adding mass to the white dwarf. And so you hit a point where it's going to collapse because it can't be stable anymore, is what it comes down to. We'll derive that in some detail. It turns out that you need the assistance of general relativity to actually make it collapse, although we won't need to know the details. Well, anyway, we'll get to that. But that's the basic idea. It's the electrons becoming relativistic that leads to Chandrasekhar limit. And if memory serves, it's one of these, this is one of these things. It's like, wow, that's amazing, and what the hell am I doing with my life? I believe he was 21 when he derived this relation. And oh my God, Yeah, it's like, right, yeah.
Looks like I'm doing nothing with my life.
Well, I guess I'm due for it.
On the other hand, that would be most of this, right? It's like I told you before about, I think, where, I showed a video about Einstein, and one of our students became depressed that she wasn't Einstein. And I'm like, well, welcome to the club.
There are very few Einsteins in the world.
There are very few, that's right. So, Chandrasekhar is just this absolute genius, as he was, what it comes down to. So, what's that?
So the Ramanujan.
Subramanian.
Ramanujan?
Subramanian Chandrasekhar.
No, I was referring to Ramanujan, the other mathematician.
Oh,
Yeah.
I see, okay.
Yeah,
Yeah. Okay,
Another
another genius. I mean, you got your Gauss, you got your Chandrasekhar, you got your Hawking, you got your Einstein,
Got your Robert Harmon.
You do, but he's realistic enough to realize that he's not going to be mentioned in the same breath, except by the people that know him. So, all right. So let's see where this works out. So let's write in. The mass-volume relation seems to imply a smooth decrease of radius with increasing mass approaching zero as the mass approaches infinity. I could be wrong. He might have been 19. I don't remember, but he was. Might have been even younger. Yeah. To imply a smooth decrease of radius with increasing mass. Actually, there's a very kind of touching story in that, he's Indian, and his mother recognized his genius, and in India at the time, there weren't the kind of opportunities he would have abroad. And so he got on a boat when he was like 19 to go to England, and in those days travel was much more difficult and it was expensive and so forth. And he never saw his mother again, and she said basically that she knew that she couldn't keep him, that the world had to have him. And so that's actually pretty touching, actually. Seems to imply a smooth decrease of radius with increasing mass. With r approaching 0 as m goes to infinity.
That's not the same person that no mentor was invited to come research with him, and he eventually passed away because he couldn't adapt to the food in England.
I think you're thinking of Ramanujan, actually. Ramanujan
It
passed
was
away.
an Indian mathematician at a very young age, who was very good, and the British scientists saw that, invited him over to research with them, and then he ended up dying really early.
That's really sad, but it's not Chandra.
That's Ramanujan.
Chandra, people, his friends call him Chandra. He lived to he died he was like 83 or something like. He died like in the 80s, maybe the early 90s. I can't remember. He was at the University of Chicago. So when I started grad school, he was still there, and so it was funny because we were just in awe of him, the grad students, and so remember one time holding the door for him, and he said, thank you. And actually, I'm going back to, back to my friends, and I said, I held the door for Chandra, and he said, thank you. Woo! And for the most part, we were like, kind of, just so intimidated, like, I can't talk to the great Chandra, I am not worthy, But I heard later that apparently he wished more grad students had would come up and, talk to him and so forth. So we should have, is what it comes down to. The one guy who would talk to him was this annoying French guy named Alex, who, yes, not Alex, Alex. Right, so he would talk to Chandra. Alex, though, he was like, oh my God. I mean, he eventually left the field so that he could swindle people out of money in business or something. And I say that not because I have something against business, but because I have something against Alex, because that's exactly what he would do.
What does it take?
I mean, he would come up with all these schemes, and he would say, in my bad French accent, but he was actually French, so he would say it with an actual French accent, he would say, if they fall for it, it is their fault. I have nothing to feel guilty for. And he meant it, so he was just like that way.
Classic French sensibility.
Yes, yes. Yeah. I have a feeling I'm going to see something like this associated with him sometime. Anyway, because he was a bit of a womanizer too. Yes, and not that he should have been, but he had a French accent in America, and that was all it took. But anyway.
Russian accent long enough.
Anyway, yeah.
Yeah, how are you doing today?
Yeah.
About to visit Soviet Union.
However, there is a maximum mass for a white dwarf. Above which the white dwarf becomes dynamically unstable to collapse. So let's consider the classical electron speed, the classical speed of an electron having the Fermi energy. So in other words, just look at the Fermi energy, set the classical kinetic energy, p squared over 2m equal to that energy to see how fast the electron would be moving if it were a classical particle. So we'll say 1/2 mv squared is equal to the Fermi energy. 1/2 mass of the electron v squared is equal to the Fermi energy. So that says the speed of the electron is twice the Fermi energy over the mass of an electron, square root, just solving for v. Well, if you put in what our prior result would be, notice P is h bar k, right? So in other words, k, and so if you set that equal to mass of the electron times its speed, then the speed of the electron would be at the Fermi energy, like if you think about the Fermi velocity, that would be h bar times k Fermi divided by the mass of the electron. And that's what I put in to get that expression for V right there. And then if we put in what the mass density should, or the number density should be, like we did before, this turns into, and if I factor out, since it's a 1/2, if I factor out the h bar squared over me squared inside the square root, I get h bar over the mass of the electron times 3 pi squared z over a rho over mh to the 1/3 power. So let's put in some numbers for an actual white dwarf. Namely, Sirius B. Yes, IB Sirius that we will use, that's totally lame. Never mind. For Sirius B, its mass is 1.053 times the sun's mass, and its radius is 550,000 kilometers. 550,000, no, that can't be it. 550,000 meters at kilometers in my nose, but that's way too big. It's because we are Earth size, so it would be like 5,500 kilometers. This yields, when you run the numbers, that V is 3.4 times 10 to the 8th power meters per second. Do you see any problem with coming up with a speed that is 3.4 times 10 to the 8th meters per second? Yes, what would be that problem? That's faster than light. Yes. Yeah, it's just a little. 3 times 10 to the 8th is the speed of light, but in other words, whoops. So what this means is that the assumption that the kinetic energy is 1/2 mv squared is wrong, because the electrons are relativistic, and so you don't get to use the classical formula for the kinetic energy. So our use of the non-relativistic formula for the speed must not be justified. So in a real white dwarf, you can clearly run into a situation where the electrons are not relative, are becoming relativistic, is what it comes down to. Not that there's a sharp line. It's not like at what speed does something become relativistic? It's a gradual. Everything is relativistic, but I don't have to explain. Anyway, so our use of the non-relativistic formula for the speed must not be justified. And in fact, it turns out that the density is at about 1 billion kilograms per cubic meter for when the electrons are becoming relativistic. you're starting to push it when you get to about 1 billion kilograms per cubic meter. Not that you want to like be anywhere near something that's got a density of 1 billion kilograms per cubic meter. Well, we will stop here because half a page is what I need to cover to get to the point, and we're not going to do that in 4 minutes. So all I would end up doing is saying, so remember last time, here's what we did, right, to get to this point. So what we're going to do is recalculate the energy using the relativistic expression for kinetic energy, and then show what happens when we take the derivative to find the pressure, and we'll see, oh, the polytropic index becomes 4/3 instead of 5/3.